个找我们还有逆转镜，给你看过这个，因为找。
Alright, shall we get started? So, we will discuss another method of ground improvement today. Particularly, it's called shallow replacement. Replacement is essentially taking problematic soil, soft clays, creeping soils, organics, highly compressible soils, and essentially replacing it with engineering fill, gravel or sand, anything that has more predictable geotechnical properties, higher strength and higher stiffness. We will look at replacement in two aspects. The first aspect is shallow replacement, and that's what we'll focus on in this module. A shallow replacement is evidently for shallow foundations. And in the latter part, we'll look at deep replacement. Deep replacement is similar to dynamic compaction methods we looked at, like vibro flot, vibro compaction. So anything that's working deeper into the ground. Now, one of the key aspects to carrying out replacement shallow foundations is to understand the different types of failure modes. One of them, of course, is the general bearing capacity failure mode. For those of you that are taking foundation engineering, I trust that you understand Terzaghis bearing capacity failure theory. If not, we can, well, I'll discuss it briefly, but we won't go into extreme details, such as deriving the formulation. I think that's strictly unnecessary because you will be given whatever equations you need anyways. But for your own understanding, and when you apply for jobs or interviews, you should still understand how the Rzagi's bearing capacity equation is derived, what are the limitations, and so forth. I will try to return your assignment marks next week. By the end of today, we should upload your assignment 2, and you have 2 weeks to complete that one. Assignment 2 is mainly on consolidation-related problems. So you should see that before the end of today. I instructed the TAs to upload it onto Moodle. And another housekeeping item, this week, Friday, is the university has canceled our classroom here because of Info Day on the 30th of Saturday. Was it 30th? 29th is Saturday, so they canceled our class this coming Friday. The classroom is gone. We're slightly ahead of schedule. I could cancel the class, or we can do it Zoom on Moodle. I don't see that we're extremely behind, and you can probably spend more time on your assignments, so I'm inclined to just cancel the class on Friday, and we continue next week. So that's the development, and I'll upload the announcement on Moodle as well. So for this module in particular, what are we worried about? Well, what are the outcomes that we expect to achieve? We want to understand how to identify when to use shallow replacement and over-excavation. We should also be able to describe the advantages and limitations of shallow replacement, or in this case, replacing soft soil with engineering fill. We should also be able to explain why this is a form of ground improvement using geotechnical principles and theory, and essentially bearing capacity theory. There are several failure modes for a shallow foundation. One of them that some of you understand quite well, Rzagi's bearing capacity, which is the general bearing capacity failure mode. And there are other types of failure modes you may not be aware of because they're less mainstream. What I mean by that, less analytical, but there are methods to calculate it. But we'll go over that as well, because if you want to do replacement, shallow replacement, you need to understand 4 failure modes and check for all 4 failure modes. Other issues, we have to identify when shallow replacement is not a suitable means of ground improvement. And last but not least, we need to be able to assess if we do carry out replacement, we are somehow distributing stress deeper into the ground. And there is, of course, an enhanced angle of stress distribution. So the last point is, how big should the area of the replacement zone actually be? So we'll try to answer and address all these questions in this particular module. Now, what is over-excavation and replacement? Well, it's essentially a fancy term for excavate, remove soil, and replace it with stronger soil. Some questions you should be asking. How much soil should we replace? That's quite important, right? Because the more soil you excavate from the ground, the more expensive it becomes. Once you excavate soil, you have to dispose of it. And disposing soil is not easy. Sometimes you have to transport it quite far away, and you're being charged per meters cubed of material that you're disposing. So the first question is, how wide is the load spreading and how deep do we have to dig into the ground so that our foundation, shallow foundation in this case, is still capable of being serviceable and withstanding ultimate limit states. As I mentioned in the beginning, the materials that we often use for replacement are very competent. We can use rock, very high strength, gravel or sand, and some of these can be called engineering fill material in Hong Kong. We can also use chemically stabilized soil. We'll talk about chemical stabilization in one of our lat term modules. Deep cement mixing is perhaps one type of chemical means. Pneumatic flow mixing is another. So the last option we have for over-excavation replacement is merging it with something that we've learned about already. We've learned about compaction. What we could do is take some in situ material, place it back and recompact it in lifts. Somehow you'll need more material because when you recompact it, your overall bulk density will change. But this is another means to do it, and then of course you can make it a bit fancier and add a bit of chemical stabilization. Lime or cement, which is a binder, to increase the strength and stiffness of soil, as we'll talk about later on. If you take a look at the schematic at the bottom of the slide here, this is a typical shallow footing. For those of you in foundation course already, I'm sure you've covered this already. So how do we denote whether something is shallow or deep? Well, general rule of thumb is if the depth of your foundation is less than or equal to the width of your footing, we generally say that's a shallow foundation. What are examples of deep foundation? Piles, right? Piles are deep foundation. So this is an example of a shallow foundation. What you see here is, we could probably assume let's assume it's a strip footing, meaning that it goes into the page infinitely, right? And what's the definition for a strip footing? Well, if your length to width ratio is greater than 5, we can assume that it's a strip footing. And if you remember from your foundations class, Terzaghi's general bearing capacity equation assumes, from a rudimentary point of view, a strip footing. Of course, it can be converted into a circular and square footing, right? But we can adjust for those using shape factors, as you'll see later on. So, generally for over-excavation replacement, what we would like to do is we need to think about this region here, particularly the soil underneath your footing. The soil underneath your footing needs to be strong enough. If it's a soft soil or clay, we want to remove it and replace it with engineering fill material. But then the question is, how thick does this fill material have to be? And to answer this question, you have to understand the prevailing failure mechanisms that can take place. And then you design the thickness and the strength of your replacement material based on overcoming these failure mechanisms. Another thing you see here is the groundwater table. Well, you can't see it now, but often if you want to carry out replacement, you need to dewater the ground. Some ways you can do it are install 2 dewatering wells, and if the groundwater table outside your excavation is here initially, then you can draw it down. Maybe sink another one here. You draw down the groundwater table so you can actually work inside the site first. So the main focus of over-excavation replacement is excavating and replacing. Now, under what circumstances is over-excavation replacement suitable? Well, there are loads of problematic soils, and we've covered this, including what you see on the slide here: loose fill, loose sand, silt, expandable soil, collapsible soil, liquefiable soil, and in colder regions you have frozen soils as well. These could excessively compress due to climate loading, due to subtle shear stresses, can even be seismic, and it can cause your shallow footing to punch through the soil. We always talk about the birthday cake analogy. So if you have your hand on a birthday cake, if the birthday cake is not strong enough, let's say you have an ice cream cake, and you just took the ice cream cake out of the freezer. It's quite strong, right? You can push down on it, but if it's a cream cake, you're probably going to push right through. So that would be your bearing capacity, the cake analogy here. So we don't want our shallow footing to punch through, or push through, or shear through our soil underneath. So any soil that you perceive as extremely low strength, you can assess this with what we talked about already, CPT or SPT. beforehand, then you probably want to excavate it and replace it. Now, there are some limitations or points we need to consider when we carry out over-excavation and replacement. Evidently, this is a very expensive method. If you have an entire site full of problematic soil, your first solution is probably not going to remove all of the soft clay on the site. This is going to be extremely expensive because anything you replace has to be replaced. And these days, if we have sand shortage, we can't just excavate. An example of over excavation would be dredging clay. If we have marine deposits in the sea, maybe a thin layer, we just want to dredge it, and so we don't have to deal with it and replace it with sand. But these days it's quite difficult to dredge because we're worried about potential environmental impacts of dredging to the seabed ecosystem, right? So there are all sorts of challenges in place. So excavation replacement is probably only quite suitable for very localized facilities. If you want to have a small building or small temporary works, then you could probably afford to excavate, or if the thickness of your problematic soil is not too deep, then you can excavate. So the general rule of thumb is we do carry out over excavation replacement for depths no longer deeper than 3 meters. Otherwise it becomes quite expensive. The advantages of over excavation and replacement is perhaps if we stay within the 3 meter range and we have 1 to 2 berms on the side, then we don't really need shoring or ELS to brace it because we're not so much worried about collapse of these retained soil sites, right? Some other limitations, if we carry out over excavation, we're probably going to induce stress release because we're removing soil. And if you have adjacent utilities, pipelines, railway tracks, buildings also founded on shallow footings, then you might cause serviceability problems and settlement to these nearby sensor receivers. So this could be one limitation of over excavation. Another challenge is if you're removing soil that's contaminated, for example, the third runway system of the Hong Kong International Airport, they were essentially building the runway right through contaminated mud pits. So if you're worried about the contaminated soil potentially releasing plumes of pollution into the ecosystem or environment, then you might not be able to use this method because excavating soils that are contaminated will probably cause you substantial headaches. Last but not least, in order to use this method, you have to have a readily available supply of fill material. If you are located in a very remote site and you're unable to transport haul trucks full of engineered fill, or it's too costly or too far away, then you're probably not going to go with over excavation replacement because it becomes economically unfeasible. So these are all engineering considerations that we need to take into account before we jump on the bandwagon of over excavation and shallow replacement. Now, in terms of application, it's of course quite limited because you're only dealing with very shallow depths of soil. But if you want to increase shallow foundation bearing capacity, of course, this is the main goal of over excavation replacement. By replacing problematic soils with something stronger, more competent, you increase the stiffness, and if you increase the stiffness of the soil, you reduce compressibility and settlement, of course, right? For problematic soils that we don't really encounter, like loess soils that expand, shrink, collapse, or freeze-thaw cycles in the northern hemisphere, this method might be useful, especially for frozen soils, which generally are susceptible to climate loading for the upper several meters, where the bottom or the deeper material is often frozen permanently. And as you can predict, we're mostly dealing with strip, square, or circular footings, which means you're probably not dealing with massive skyscrapers because you're not transmitting significant loads to the soil here. So anything with shallow footings, And anything shallow, of course, is synonymous with highway and railway construction embankments. We can often remove portions of problematic soil if we're going to have a railway line alignment that cuts through problematic areas. If it's not too deep, we can replace this problematic soil. So these are potential applications. Later on in the next module, when we talk about deep replacement, this is perhaps more suitable for places like Hong Kong, especially when we need to rapidly strengthen marine deposits so we can create land to build on top of. Over the past couple of slides, I've hinted at potential strengths and weaknesses of over-excavation and shallow replacement. This is, well, it can be cost effective if you only have a small area to replace, but if you have a massive site, it's not economically feasible, right? So it's cost effective if you have a very small area to replace, you can ship in fill material, and it's easy for you to dispose the soil. For example, we talked about if you don't have to dispose contaminated soil, it becomes a lot easier, right? In some places around the world, what they do is they take the problematic soil, could be clay, they inject cement or some binder into it. They also inject compressed air into it. They mix it up, and then they replace it back into whatever they dig up. And this mixture of problematic soil, binder, could be cement, lime, slag, and compressed air, becomes a new type of fill material that you can use for construction because it gains strength due to the addition of binder, right? We call this pneumatic flow mixing. Some parts of in Japan, their airports were reclaimed solely by pneumatic flow mixing, by excavating, strengthening, and replacing. It's called pneumatic because we use compressed air to transport this mixed material through pipes as well. Another advantage of over-excavation replacement is it doesn't require specialist contractors. We're just excavating material and doing simple bearing capacity calculations and checking if shallow footings will be fine. So we don't need to bring in special equipment, special mixers, special rigs for the task. Also, we mentioned that since we're dealing with depths that are less than 3 meters in depth, if we cut berms on both sides, then we don't need any shoring, we don't need any ELS to protect our workers, and it's quite simple to dewater to depths of 3 meters. You just need to sink in a few dewatering wells. Now, those are perhaps the advantages of over-excavation replacement. Now, limitations. In some places, you might not be able to bring in excavation equipment. You need an excavator to remove soil. If you have construction right next to the sea, you have a constant recharge from the sea, and it might be difficult to dewater to a certain elevation that you need without maybe sinking some sheet pile walls in, right? Or a better hydraulic cutoff. So high groundwater tables could make over-excavation and shallow replacement not work too well. And as we mentioned, if you have adjacent sensitive receivers nearby, utility lines like gas mains, buildings also found on shallow footings, you might induce stress release and settlement to these buildings, causing cracks or serviceability problems. And synonymous with the need for quality engineering fill, if you don't have access to the site, you don't have haul roads, you don't have transportation, then you can't replace because you don't have any replacement material. Likewise, if you don't have fill material or it's too expensive, like sand, gravel, and you cannot carry out replacement. So if all of these circumstances happen, then you probably need to look at an alternative, such as chemical improvements, preloading, and so forth. You can still bring in concrete blocks or something. So notice that we've covered several methods for ground improvement so far, so you need to sometimes think about which method suits a particular construction site. That's your job as a geotechnical engineer. So another question that we have to answer is, what is the extent of replacement? How much material do we need to replace? How wide of a site we need to replace? Do we have to entirely remove all the soil and replace with engineering fill, or can we only partially remove the soil? Can we mix it with the binder, dump it back in? So it depends on what's a more economic approach based on the advantages and limitations that we discussed previously. For special soils that we talked about, expansive, collapsible, frozen soils, you just want to replace everything to depth where you don't have to deal with these problematic soils. This is quite obvious, right? Same with the width. For loose fill material, loose sand and silt, soft soils, your depth and width of excavation needs to exceed, well, basically 4 failure modes that we'll talk about in the following slides. We're concerned about 4 potential failure modes, and if we can overcome these 4 failure modes and we do some calculations, then that would be the limiting factor for your depth and width. So these are the aspects we'll talk about in the forthcoming slides. So let's jump into the topic at hand. For any footing, let's define some basics first. So we often want to deal with the net pressure. And what's the net pressure? Well, if you look at the schematic here, you have some force applied to a shallow footing. The net pressure is all the applied and the difference between the applied and the resisting forces. So you can see here in this equation, you have applied force P here, you have the weight of the footing itself distributed over the area of the footing, and we subtract the contributions from the effective overburden, essentially the effective stress propping up this footing. And the effective stress is of course calculated based on the unit weight times some depth of your footing, right? So this is what we refer to net pressure applied to the base of the footing. Now, if you look at the schematic, it's quite interesting. When we talk about the extent of replacement, we know based on soil mechanics that when you apply some stress to the ground, we often distribute loading at some particular angle, theta here. So when we distribute the loading, what happens? Well, the applied area becomes larger. So we can see that the width, originally called width of footing, B subscript F, becomes B subscript RZ, which stands for replacement zone. This is, of course, your net pressure, Pn here. H subscript R is your height of replacement zone. So we need to calculate all 4 failure modes that we'll discuss to determine what the height of replacement is, what the width of the replacement zone is, so we know how much to excavate. And we often do this before we do this on site, so we know whether it's economically feasible. If we have to excavate a zone that's too wide or too deep, then perhaps we'll stop there because it doesn't make sense to use this approach. So this is just a quick review. This is the net pressure at the base of a footing. Now, to further expound on the concept of stress distribution, we can assess the additional vertical stress for a rectangular footing. Now, and that's what's shown in the green here, delta sigma z. And this delta sigma z is generally, we assume it to be at the center and the bottom of the replaced zone. So we would say this is the replaced zone here, right? This is the replaced zone, this is the original, or we can call it in situ soil. Outside of the zone, so we can make a different color. This is the in situ soil. And since the soil above the footing only contributes an overburden, you can sometimes throw the in situ soil back on top. So only the red part is the new engineering fill material that we prop in to the site. Now, for this particular problem, it's purely geometrical. What do I mean by that? Well, we know the net stress here, and we can use a ratio of areas here. So area of the footing is here, and area of the replacement zone would be B times some length into the page of the replacement zone. Gives you your area F prime. Prime denotes the replacement zone area. So the stress is distributed to a larger area, and that's the point of carrying over replacement using a more competent soil. So you can see that the initial area of the footing is the base of the footing, which is here, times the length of the footing. Depends if you have a strip or a square footing. And this is the length and width of the replacement zone area. So some area, you draw in 3D inside the page here. And you can define L prime and B prime using just trigonometry based on HR and some replacement angle. So we'll talk about load distribution angle later on. But the load distribution angle mainly depends on the failure mode, and we'll talk about how to estimate or assess that. So all the variables here are describing a rectangular footing. If you describe circular footing, then of course your length scales will change. You'll probably use the diameter, right? So for example, if you want to change this to a circular footing, we're looking at the diameter of, if you look on plan view, this would be your diameter, and this is the diameter of the replaced zone. And you can calculate it also based on trig, based on your height of replacement zone, some load distribution angle, which we'll talk about later on. If you're dealing with a continuous or strip footing, then we only care about the width, right? Because everything is unit run into the page. So you have some net stress over a ratio of areas. So that's the change in applied stress. So those are the basics that I want to get out of the way first. Now, I talked about 4 potential failure modes that we need to consider. This first one in the red box here is something that you should be familiar with if you've taken foundation engineering. If not, I will quickly or briefly go over some basics of bearing capacity. So if you've taken bearing capacity related modules, you would know that we often learn Terzagh's bearing capacity theory for a strip footing. We'll talk about this. So this is the typical failure mechanism that we assume originates from Crandall in 1921, and Terzaghi modified it for soil. We'll talk about that in a bit. So that's a general bearing capacity failure mode. Essentially what you see in these 4 schematics are different failure mechanisms. And based on the mechanism, we can use fundamental force balance equations, for example, moment balance, to calculate whether we expect failure or not. So we call this failure mode general bearing capacity failure. General capacity bearing capacity failure follows this particular shear mode that you see on the slide. So that's the first one. We'll talk about each one consecutively. Some other failure modes that we'll talk about include this one here, which is not something you deal with from day to day. If this is the replacement material here, what can happen is you form some sort of plug to punch right through the soil, punch right through the replacement material, and then you get general failure, right? So anything outside the hashed red area is your in situ problematic soil. So even if you do replacement in this red box here, this box here is the replaced soil. Even if you replace this box, you can still get bearing capacity failure underneath your replaced soil if you don't cater for punching failure. So we call this punching failure through the replacement zone. So that's another mechanism that we'll consider. Likewise, you can also, this is your replaced zone, okay, in this box here. you can get bearing capacity of your replaced zone. We're not looking at bearing capacity of the in situ soil because we're doing replacement. Evidently, the in situ soil wasn't strong enough. That's why we had to replace it in the first place. Okay, so just a quick summary. This mechanism here is just a general bearing capacity failure of the replaced zone. This mechanism here is you form some sort of punch right through the replaced zone, and you get general bearing capacity failure underneath the punch zone in situ soil. Another potential mechanism is you don't punch right through. Punching right through would mean you have almost vertical punch through zone here, but you can also distribute load through the replacement zone and then get bearing capacity failure. So that's another mode of failure that we need to account for. We call this failure of a distributed foundation. So when we talk about foundation, we consider this replaced zone to be part of the foundation along with the shallow footing. Because we, as a geotechnical engineers, engineered the replacement zone, so we consider that as part of the foundation. That's why we say failure of the distributed foundation. In terms of parameters, nothing much has changed here. In the last failure mode that we'll look at, we have a punching failure of the replaced zone. And what happens here is you don't even have to worry about, in this case, you have a plug forming in here. You don't have to worry about the plug. The problem here is the replaced zone here wasn't wide enough. So this is one of the extents, the width of the replacement zone. And what happened was you just basically increased the size of your footing and the weight of your footing, and you punched through the soil underneath, and you caused general bearing capacity failure. So that's the last mode, punching failure, replaced zone. And if you look at these four modes carefully, you'll notice something that's the same for all four. We do have to assess general bearing capacity failure for each of these modes. For punch zone, you can imagine that there's some passive resistance here propping up this plug, right? So we always come back to basic zone mechanics. I uploaded some basic materials on ranking earth pressure theory, so we always come back to passive resistance. You can imagine that when you push down on this, there has to be something holding this plug together. Likewise, anytime you form a plug, there has to be passive horizontal stress holding this plug together. So if we'll go through this bit by bit in the following slides. So before we do calculations or look at mathematics involved, at the bottom of the slide there are some options you can do empirically to prevent these four failure modes. We can use geosynthetics. We'll talk about what geosynthetics are in the forthcoming lectures. You can just change the area of the foundation, right? You can make your footing much wider. You distribute the stresses, and you might not need to do replacement at all, right? If you increase your footing size, let's say something much wider, you solve yourself a lot of headaches, right? But then you have a much wider footing. You can use stronger fill or a thicker fill layer. So usually for fill, it's drain material, and we just look at it in terms of some phi dash. We can find a fill material with a very high friction angle. That would help, right? If it's not just 30, if it's like 40, 45, very coarse gravel material, we can minimize the effects of these failure modes. Last but not least, just reduce the load. So if you have some load P here, don't have such a high load, have more footings, distribute the loads on the footings, then you don't have to carry out replacement. So these are engineering options, quite common sense, right? In terms of design considerations, there are a few things that we need to consider based on these four modes. We have to find out what's HR, how deep should we have it so we can overcome these four failure modes. what's the width of the replacement zone. The width matters, right? Because if you look at this failure mechanism, this replaced area became part of the footing, and it just punched through the soil underneath. So we need to decide what's the depth and width of replacement, and of course, as I talked about, what's the strength of the material to prevent serviceability and ultimate limit state problems. That's why we talk about strength and modulus of the fill material. So we'll go over these aspects in the coming slides. Now, this is not really a quick review. I think we should talk about this a bit more. So, there are different bearing capacity equations. The one we're most familiar with from an undergraduate level that we often explain to you is Terzaghi's bearing capacity equation. Can it be generalized? Well, yeah, it can. The one that we will use in our module is generalized. I'll give you the equations, I'll give you all the factors, so you don't have to memorize anything. But I do want to talk about where these equations come from. If not, at least let's talk about Terzaghi's bearing capacity equation. So there's some points I want to write down. For example, I want you to know that there are many different bearing capacity equations from different researchers and engineers. What we're using is a generalized form. The most rudimentary one is Terzaghi. So there are a lot of bearing capacity equations that we can use. All of them are based on limiting equilibrium. The one that we often like to teach our undergrads, Terzaghi, 1943 for strip footing. So I'll spend some time to talk about this one. Other ones are Besic, Meerhoff. So we also have Meerhoff. 1963. We have Hansen, 1970, and Besic, 1973. Now, you're thinking, are these bearing capacity equations different from these four authors? They're slightly different, but not substantially. For example, Besic will assume maybe a different angle for the failure mechanisms. Instead of phi dash for Terzaghi's general bearing capacity equation, he assumes phi dash plus 45 over 2 because this angle was proven using field observations and experiments. So are they fundamentally different? Not really. So that's why we can generalize the equation. So what you see here is a very generalized equation. The one you're probably used to seeing seeing this form probably, right? And so you're asking, what are all these other things here? The reason I decided to use this is because I think it's quite confusing with so many shape factors, so many different NQ values, so many different NC and gamma values. So normally in undergraduate textbooks, we see this as equation for strip footings, right? And I guess in your other classes you probably get a nice table to extract your NQ and gamma NC values as well. And you have to be quite clever, right? Because they may give you a table for strip footing, a table for square footing, and a table for circular footing, right? So anyways, let me break this down a bit more. So depending on the shape of your footing, whether it's circle, square, I'll show you some just quick conversions later. These are estimates, of course. And whether it's embedded, what's the embedment depth over top? Then you have embedment depth factors, DC, DQ, D gamma. If you want to make this more complicated, you can also have incline loading on your footing. Then you have I, C, IQ, I gamma, right? So we call this shape and depth factors, right? Q, of course, is just some unit weight times that. Now, with any footing, what happens initially when you load it? Well, when you initially load it, you get, well, a very small elastic response, but then everything becomes plastic right away. And if you try to load it some more, you just get settlement without any more resistance. That's why the load just drops off. So this is what happens when you keep on loading footing, right? And let's talk about this from Terzagh's bearing capacity equation. So let me do this. So just a quick recap. So let's focus particularly on Terzagh's bearing capacity equation. So because most of the other ones are based off this anyways, so we call this Terzagh's ultimate bearing capacity equation. So Terzagh's bearing capacity equation was, just a recap, originally borrowed from Prandtl, right? So Prandtl So this person essentially modeled a metal object penetrating into softer material. And then it was Terzaghi that borrowed this concept in about 1943 to extend it for a footing on soil, right? So we mentioned a few things. There are a few assumptions that we need to assess. So we talked about this already. Terzaghi originally derived his formulation for strip footings, right? So length to width ratio has to be greater than 5. So this is length. Good. And it's also for shallow footings. So the definition of shallow footing is we have footing here. We have some depth, df, b, the width of your footing. So as long as your df is less than or equal to b, then we can say that's a shallow footing. Another assumption that Terzaghi made was we assume the weight of the soil above the base of the footing may be replaced by a uniform surcharge. So what am I talking about? Well, let's draw his failure mechanism out because all 4 failure modes have general bearing capacity failures. So Terzaghi's failure mode looks something like this. So there's some embedment here. apply. Load per unit area. We have some depth, df, footing, and we assume that the surcharge can just be some unit weight times df. So the failure mode that we're interested in here is essentially we have one region here, two other regions here. So let's call this zone 1. Let's call these zone 2. Call these zone 3. So I'm not going to go into too much detail, but we'll talk about general failure mechanisms. So zone 1 is, let's say it's some elastic zone. Zone 2, let's call it a radial shear zone. Zone 3, ranking as the zone. And then if we look at these two pink lines here, we can say that these are just logarithmic spiral curves. Okay, so why am I showing you this failure mechanism? Well, anything in engineering requires mechanism. We need to draw it out. Or how does it move when it fits, right? How does the soil fail? Before we can come up with some analytical approaches to characterize this failure mechanism. This particular failure mode requires an assumption that your soil is linear elastic, partly plastic, right? So initially loading the soil, you get some elastic response that's recoverable, and if you keep on applying displacement of the footing, your soil will become perfectly plastic eventually. Okay, it looks like I'm out of time. We'll carry on in the next class then. Please do your assignment too. It will be released on Moodle today, and we'll release your grades hopefully in a week. So good. I'll see you in next class. Next class is canceled because of info day. So I'll put an announcement on Moodle so you don't forget. So next class will be Tuesday. Thank you. You want me to not close it yet? I'll give up now.